Hello, everyone. In this particular video, we're going to start talking about ethers. Ethers are a new functional group that we'll be learning. And these molecules are characterized by an oxygen that's sandwiched between two carbon-containing groups. So the functional group is this oxygen. Contrast this structure to the alcohol, where you have one alkyl group and then a hydrogen, right? That's an alcohol. So this is an ether. On the other hand, alcohols are sort of similar in structure, where one of the alkyl groups is replaced by a hydrogen. So we'll start our discussion by talking about the synthesis of ethers. How do we access these molecules? How are these synthesized, or how are these produced? We'll look at a couple of methods. The first one is going to be the dehydration of alcohols. Okay. Now, the reason we're talking about this method is because this method is used for the industrial production of diethyl ether. So a little bit of nomenclature here. Look at that. That's an ether with two alkyl groups. And if you notice, there are two carbon chains on both sides. A two carbon chain is an ethyl group. So the name of this molecule is diethyl ether. Okay, because you have it's a common name. It's not an IUPAC name, but the common name of this molecule is diethyl ether. Now, diethyl ether is used as a solvent in a lot of reactions. So whenever we talk about organic reactions, and if you see ether mentioned, it is referring to the diethyl ether. In most instances, there's also petroleum ether, but diethyl ether is the most common solvent that's used when we refer to as ether. Okay, so let's look at how this is synthesized. So industrially, diethyl ether is synthesized by the dehydration of ethanol. So if you take two molecules of ethanol and you dehydrate it, now, since this is a dehydration, you would need a strong acid for doing this. And overall, you're going to lose a molecule of water. That's the dehydration. So when you do that, you get diethyl ether as your byproduct here. Okay, how would the reaction work? Mechanistically, can you imagine that in presence of an acid, the alcohol gets protonated? Okay, so we can use a hydronium ion to represent acid. So the alcohol oxygen will get protonated under these conditions because we are operating under acidic conditions. And by doing so, what we've done is we've converted this bad leaving group, okay, that's a bad leaving group, into a good leaving group. And we'll make water along with this. Okay, from the hydronium ion, you're going to get water because the proton was picked up by the alcohol. So that's under equilibrium. And once this happens, we could have the next step where the second molecule of the alcohol, so we need two molecules of alcohol for this reaction here. So the second molecule of the alcohol can use its lone pair to come and attack this carbon, which notice is the alpha carbon because that's connected to the functional group. So the second molecule of the alcohol can use its lone pair to do a nucleophilic attack. So that's an SN2-like attack here. And simultaneously, the water molecule is going to lead. So by the end of this, what we would have is this structure here, okay, where that alcohol is connected to this ethyl group through that oxygen atom. The oxygen atom has one lone pair and the hydrogen on it. It has a positive charge, a formal charge. And plus, we are going to make water here. Okay. And again, at this stage here, it is very likely that the water molecule can go and attack one of these alpha carbons and take us back. So that means this process is also going to be under equilibrium because it can go forward and backward. Okay, it is a reversible reaction, so it is going to reach equilibrium at some point. And then in the final step, the water molecule here can go and deprotonate that hydrogen, okay, or deprotonate the species here to give us the ether, diethyl ether, and this step is also reversible, plus H3O plus. So we regenerate our acid here, okay? So we started by using a hydronium ion. Notice this is hydronium ion, that's what we've written here. And so we started by consuming a hydronium ion or consuming a proton, and in the end, we've regenerated that acid. So that means this reaction is acid catalyzed, okay? This is another example of a reaction that is catalyzed by acid. What that means is you don't really need a lot of acid for doing this reaction because the acid gets used up initially and it's generated at the end. Okay, so it sort of gets repurposed again and again. You recycle it, so it's a reversible reaction, and so you only need a catalytic, a small amount of acid. Acid catalyzed, implying that you need small amounts of acid for doing this reaction. Okay, so that's one method. And like I mentioned, the significance of this method is that it is used for the industrial preparation of diethyl ether, which is a bulk solvent that's used in organic chemistry. Okay, let's look at the second method. Okay, so the second method for synthesizing ethers is called the Williamsons ether synthesis. Okay, it's called the Williamsons ether synthesis. This would allow us to use a little bit of retrosynthetic analysis again when we are done with it. But what the Williamsons ether synthesis involves is the attack of an alkoxide on an alkyl halide. Okay, it involves the attack of an alkoxide on an alkyl halide. What does that mean? An alkoxide is actually, I'm going to make it much simpler. Okay, an alkoxide is the species. Okay, this is the conjugate base of an alcohol. That's what this is. An alkyl halide, as we know, is Rx. Okay, so you can react an alkoxide with an alkyl halide to make an ether. Now, how do you make the alkoxide? Since this is the conjugate base of an alcohol, what you can do is you can start with an alcohol and react it with a base. Okay, so if you react a an alcohol with a base, and I think a very common base could be sodium hydride. You could even use sodium for doing this reaction, or just sodium metal. Okay, if you do that, then at least with the sodium hydride, you can see that the hydride would come and deprotonate this hydrogen, and the electrons would go to the oxygen. The oxygen had 2 lone pairs already, so that gives us the alkoxide. So the alkoxide can be synthesized from an alcohol, and then when the alkoxide attacks an alkyl halide, that gives you the ether product. Okay, so what would a general scheme look like? Let's write that down. So if I start with an alcohol, you can first deprotonate it to make an alkoxide. Okay, so alcohol is deprotonated to make the alkoxide, and then the alkoxide reacts with, let's say, another alkyl halide. I'm putting R prime to sort of differentiate this R from that R, but they could be the same R, okay, irrespective, but differentiating that. So when you react it with an alkyl halide, this alkoxide would do an SN2 kind of an attack, and the halide would be kicked out so that it would give us ROR prime plus X minus. So we can synthesize the ether that way. Okay, so we can start from an alcohol, deprotonate to an alkoxide, and then attack an alkyl halide to make the ether product. Let's look at a specific example. Okay, so let's say if I start with ethanol, okay, I can react ethanol with sodium hydride, Na plus, H minus. Sodium hydride, we've talked about this before. This is a base. It's a strong base, but it's not a good nucleophile, okay? So when we wanted hydride as a nucleophile, we used sodium borohydride or lithium aluminum hydride. Okay, but sodium borohydride is a very good base. So it will come and deprotonate, electrons go here. It will give us the alkoxide. Obviously, the sodium is going to be here, balancing the charge. I sort of left that out here, but the sodium is going to be balancing the charge here. And now, after this, if I react it with methyl bromide, let's say, an example of an alkyl halide, this is going to go and attack that carbon. The Br is going to leave. So in the end, I will make an ether with sodium bromide as the byproduct. So the sodium now goes with the Br minus that's coming out. So we get the sodium bromide as the byproduct. Now, this attack here is an SN2 attack. Okay, this is an SN2 attack that's happening here. And that has implications, because now you have to think about, okay, what sort of alkyl halides participate in SN2 reactions, right? So since this is an SN2 attack, this applies to methyl primary and secondary alkyl halides. And in fact, in that order, okay, so methyl alkyl halides would be the most reactive, and then primary, and then secondary. Tertiary alkyl halides do not participate in SN2 reactions. So that still applies. So you cannot make an alkoxide and use a tertiary alkyl halide hoping to make an ether there. If you use an alkoxide, which is a strong nucleophile and also a strong base, with a tertiary alkyl halide, it's going to give you elimination instead because it's a strong base as well, okay? Now, using that information, we can actually do some sort of a retrosynthesis. Think about, okay, what would be an appropriate starting material for making a particular ether? So let's look at an example of that. So let's say we want to make a particular ether, okay? And this example is for retrosynthesis. Okay. It's an example to demonstrate retrosynthesis as applied to Williamsons ether synthesis. So let's say we want to make this ether. That's our product. We want this ether. Now, as far as this ether is concerned, look at the mechanism here. The alkoxide, okay, which contains one of the R groups, attacks an alkyl halide to give us the product ether so that the oxygen is between the two alkyl groups. So that means for this particular ether, you can imagine two disconnections, essentially, two possibilities for starting materials. One possibility is that this was the bond that was formed, okay? And so when you're breaking here, if the oxygen is with that chain, that means this part came in as the alkoxide and the other part was the alkyl halide, okay? So one possibility is that this ether can be made from an alkyl halide like that. So since the oxygen is on the other side of this disconnection that I made, I'm going to add the halogen to this carbon here, okay? Plus, the other part is the alkoxide. Like that. That's one disconnection. And again, since I have the O- here, this must be with some cation to stabilize that charge. So that's one disconnection possibility. The other possibility for a disconnection is that, okay, this bond was cleaved. Now when you cleave, or this bond was formed when you're going forward. So if that bond was formed, then notice how the oxygen is along with this isopropyl portion. And so the other disconnection possibility is that you started with the isopropoxide as a nucleophile, or this was the alkoxide. And then the other portion, which is the two carbon chain, was the alkyl halide. Some halogen, chlorine, bromine, iodine. Again, this is an SN2, so we will not use fluorides, alkyl fluorides. They do not participate in SN2 reactions, okay? But the chlorides, bromides, iodides, they are all fine. So we sort of derive two possibilities for a nucleophilic or for an SN2 reaction here, okay? Now we can analyze both of these. And if I analyze the first one, what I notice is we have a secondary alkyl halide here with a strong nucleophile. SN2 reaction is possible. If I analyze the second scenario here, we have a primary alkyl halide. And so now the question is, which one of these two, okay, which combination is better for SN2? Is it the first one or is it the second one? And as we just said, SN2 reactions work best with methyl halides, and the next alkyl halide that will do it best is the primary alkyl halide. So between the two alkyl halide possibilities here, the primary alkyl halide is going to give us a better SN2 reaction. A secondary alkyl halide can still give you an SN2, but you would also see competing E2 reaction. So that means for making this ether product, the better combination is the second option, okay? This is going to be the option of choice. That would give us a better product, or like more yield, more product. It's a better reaction to do. Okay, so with Williamsons synthesis, we can actually do some retrosynthesis and actually identify and determine, which combination of the alkoxide and the alkyl halide would be better for doing this reaction. Now, if this is the alkoxide, the alcohol that it would be made from is going to be ethanol. All you have to do is remove that negative charge, add a hydrogen to it, and you get the alcohol. If this is the alkoxide, then the alcohol would be isopropanol. Remove that negative charge, one lone pair, and add a hydrogen, and you've gotten the alcohol that you would need. Okay, so that's the retrosynthesis as applied to the Williamsons ether synthesis. And Williamsons ether synthesis, I would say this is I guess the most common way of synthesizing ethers. Okay, let's look at a third method very quickly, because this is we've already seen this method of synthesizing ethers. Okay, so a third synthesis for ethers is the oxymercuration-demercuration reaction. We've looked at this reaction prior when we were talking about the reactions of alkenes. And essentially what happens in this reaction is you can start from an alkene, you react it with mercuric acetate, and the ether that will be formed really depends on the solvent that's going to be used here. So if you use an alcohol as your solvent there, followed by a reduction using sodium borohydride, if we do this, then our product is going to be an OR prime. So notice again, the oxygen is between two carbon atoms, carbon-containing groups. So that's an ether. So this is another method of synthesizing ether. Okay. So using alcohols as solvents in oxymercuration-demercuration offers an ether as the product. If water is used as a solvent here, then the product is going to be an alcohol. The mechanism is the same. Nothing is different here, but just by changing the solvent from water to an alcohol, you can change the product to an ether. So those are all the syntheses of ethers that we are covering right now. So we talked about the dehydration of alcohols, the Williamsons ether synthesis, and oxymercuration-demercuration. If you're interested in learning more about the mechanism of the oxymercuration-demercuration, please refer to a separate video, a different video in the alkenes content area. Bye.